So let's now take a look at this circuit, but let's give the battery some internal resistance. Now, as I've said before, we don't normally know what the internal resistance of a battery is. We have to measure it, but in this case, we do know what it is. So you can see what effect that's going to have on the circuit. So instead of having a total resistance of 3 ohms, we've now got internal resistance that's adding to the total resistance of the circuit. So that's going to affect the current going through. So I'm going to include this one and show the workings, but again, I'll stress we don't normally know what it is, but we're going to have a look at the effect. So the first thing, the total resistance of this circuit is now, so we've got 1 ohm plus 2 ohm plus another 2 ohm. So that gives us a total of 5 ohms resistance. We've got our voltage, total voltage is 1.5 volt. So now we can use Ohm's law, knowing these values here, we can rearrange this and we've got 1.5 volts over a total resistance of 5, and that will give us 0.3 amps. Now that's less than what it was without the internal resistance, and that's what you'd expect because you're adding more resistance. So the total resistance of the circuit is increasing, therefore the current must be decreasing. If we close the circuit now and see how that works out, okay, so 0.3 amps of current going through. So let's now have a look at the effect that this has on the voltage drops across all the resistors. So we consider the internal resistance as one of the resistors in series. So there's going to be a voltage drop across the internal resistance, across the first resistor, external resistor, and the second external resistor. And we've got the same rule that applies in terms of the voltage, that the total voltage equals the sum of the voltage drops across each of these resistors. Okay, so let's deal with our voltages. So the sum of the total voltage equals the voltage across the first resistor plus the voltage across the second resistor plus the voltage across the internal resistance. We can say that that equals the current times the resistance of the first resistor, of the second, and of the internal resistance. So these are what we want to calculate. So we know the current and we know the resistances, so we should be able to work out what each of those voltages are. The second one, third one, which is the internal resistance. Now we do a check. Do these add up to 1.5? So that's 1.2 plus 0.3 is 1.5. Okay, and that's a good check. But I hear you ask, what if we didn't know what the internal resistance was? So let's say that was an unknown. We can still measure the circuit current, so that would be a known. We can measure these using our multimeters, so they'd also be known. And this value here, which as we've looked at it previously, is our open circuit voltage. So we know what that is. So this is the point where we'd say that using Kirchhoff's law, we'd be able to work out that the open circuit voltage is should equal that plus that plus that. Okay, and then we can rearrange it. So we end up with 1.5 minus 0.3 minus 0.6, which should leave us with 0.6 volts as the voltage drop due to the internal resistance. And then you just come back to here, well, that equals your current, which is known, times that, so we rearrange it, and that leaves us with a resistance of 2 ohms. So I'm going to leave this video here at this point, and the next video will then look at it in terms of a parallel circuit. So we're going to look at the effective internal resistance of batteries on this type of circuit. So it will get a little bit more challenging, but we'll bring it back to looking at without internal resistance, so an ideal battery source, and then compare it to having internal resistance, because now we've got 2 branches.